Okay. Hi, guys. This is meant to be a little bit of a different type of talk. It's not meant to become a product pitch or any kind of product background, but just a few thoughts in terms of something we kind of think about when we do stuff in our company, which is, a lot of the big data kind of topics are targeted at data streams that come out from kind of a procedural kind of analytics environment, as opposed to kind of taking the human element into big data. And what I'm trying to say with this talk is, try to open your mind more about what are dimensions of big data out there, which you can use similar tools and similar methodologies for processing, as opposed to just going through click streams, social media, and so on, right? So Mozart, not my first choice. Would have preferred to do Bach. Mathematically easier to process, but I think Mozart is more famous and more known. Not much we have to say. He's a guy, child prodigy, very prolific, over 600 works, considered one of the founders of the classical music before Haydn, and clearly he is kind of one of the composers that kind of does two things. He writes for the mass as much as he writes for the scientist. So if you're a music scientist, you will love him. If you are a common person in the audience, you will love him. Kind of one of those geniuses which kind of strikes a balance between both audiences. What I'm trying to say and what I'm trying to show today is take one piece of his body of work and analyze it down in terms of what is the scope of his choice in producing that piece of work. So for instance, if you're Amazon, you have a click stream and you run machine learning over that is billions and maybe trillions of data sets. When he makes choices on writing a piece of work, the number of choices he has and the kind of the neural algorithms that his brain goes through to choose things are infinitesimally higher than what the big data, what we call big data, is really small data compared to what this guy and his brain has to process to make creative choices, right? So let's take one piece, which I guess is one of his more well-known pieces. He wrote that in his last year before he died. It was performed in 1791, and we know it's a lot of stuff going on in that opera. But if you say, if I'm the composer and I'm trying to make choices along the path of creating each line of music, what are the choices that are available? How do I create the framework that I use to make these choices? So let's just look at the musical dimension of his work or this specific opera. So obviously, I don't know how many people in the audience are musically versed. You have a notation system which kind of scrolls horizontally, and it's kind of a timeline. So for each time bar, you get like a number of notes in that bar. You have a time signature, which means how many beats that bar would have available. So in this case, the signature is 4/4, which means that for each bar, so this is a bar here, you have 4/4 available. So you could have a different time signature, and then you have more bars or less bars available in that time. And obviously, along the score, you have different instruments that you use. So, for traditionally in that period, you would have a small chamber orchestra that performs these things. So the instrumentation from the flutes down to the reeds, and in later parts is the overture, which is basically the beginning of the opera. And later you have obviously also the singing voices. And each time you have a voicing that basically is played by an instrument. So from his perspective, he sits down and starts to make what we as data scientists call quantitative choices, right? Do I put a note here, down here? Do I use a different instrument? Do I use a parallel voicing for different violins? So these are all metrics that his brain has to decide. And on what basis does the brain, the creative process in one's brain decide when to choose what and what scope comes out from that if you multiply out what the options are that he has available. The additional layers of choice that come with that, because if you are writing for the violin, you can write in a scale or in a certain, call it a note bandwidth, within which that instrument can play. So you still have a choice where to position that instrument in terms of the pitch. You can say, I want to play it at C4, which is kind of half on the keyboard if you look at the keyboard, or you can say, I want to play it up very high. Again, these are creative choices his brain makes, but they are infinitesimal because if you see afterwards, the numbers that come with that are huge. So let's just look quickly, just trying to multiply out what are the numbers that he has available when he makes these choices. So this is the opera. These are the sections. Each section has a certain time signature, has certain bars that he decided to set, and the corresponding beats. So you end up with a number of beats that that piece of work has. You then add the chromatic range for each instrument, so which was this, and you say, certain instruments can play a wide or a less wide chromatic range. So for instance, the timpani, the things that look like drums, only have a very limited chromatic range because that's the nature of the drum. You then subjectively apply a style range factor because obviously the composer composes in a certain time period. So stylistically, he's confined within certain limitations of that particular time. If you would have Schoenberg and let's say 12-tone music of today, this chromatic range would be 1 because a 12-tone musician would be able to write in any chromatic note he wants. But Mozart, obviously, in his style, let's say 0.5, which is a guess. Secondly, you have the density factors of each instrument. So within each voicing, with each line, this instrument can have a certain density of playing on the beats. So for instance, a string instrument would play faster than let's say a reed instrument. So we would have the passes of a violin would go faster on average than a reed instrument. So we assign, there we go. We assign a factor to multiply out the density that can occur within each bar of that instrument. You have a voice factor, because different instruments occur different times in the piece. And you have a coverage factor, which is an additional, let's say, subjective guesstimate based on his style and his piece, what the available range he had for each specific instrument over the course of that piece. Because, for instance, obviously, a singing voice occurs much less than an instrument. You would always find like a cello and a bass pretty much everywhere, but you only occur, the singer itself only occurs at a certain point. So, long story short, if you multiply all this out, we don't talk about trillion data sets, we talk a sextillion and more, because this is a very, very limited cut of the quantitative choice that his brain makes at every time he composes a piece. So the whole point about big data and MapReduce, my contention here is to saying that our brains use similar algorithms that we can compare when we look at using MapReduce, the big data kind of technologies on our traditional data set. But can we create a parallel between what somebody like a creative brain like Mozart does versus what we do in terms of processing click streams and social media, etc.? So let's assume that we want to go down the MapReduce route. The first thing we have to think about in terms of how our brains work is clearly that our brains are not computers. So we don't use the same parallel CPU-driven processes what we would do if you run a Hadoop cluster. in fact, when you look at our neurons, then a neuron has a firing refresh max rate of around 5 milliseconds. That means that when the neuron takes in the data from the synapses attached to the neuron, it takes a maximum of 5 milliseconds before it can refresh or firing a signal out to other neurons. That means if you look at a cascading element and you say like you have, for instance, like 100 neurons, that's half a second of our brain processing stuff, right? So let's take an example of you looking at a picture and you being asked, tell me if there's a cat inside the picture or not. An average person probably can do like half a second. Any computer would take a much, much longer time than that. But given that our neurons only fire at a maximum of 5 milliseconds, how many neurons do we have? Well, we have 100 neurons available to fire, which means that that thought process goes down in half a second, and we have a limited amount of neurons available to process the same stuff what a Hadoop cluster, in terms of visual analytics, would have to do over, I don't know how many clusters you need, but it depends on the CPU and everything. But clearly, our brain is built differently than a traditional big data environment. So, and I'm sure you all know Jeff Hawkins, the founder of Palm and now Numenta. He comes up with a theory that our brains are basically memory systems. They're not processing systems, they're memory systems. So what we do is like we create prototype reference systems. So when I look at faces, each face of this audience is approximately based on a prototype I've stored. So when my brain recalls a prototype, I compare the delta difference between my prototype I've stored and you as a difference of a face, which allows my brain to only store and process the delta difference between what's stored and what I see new. So let's put this aside for a second. So we talked about Mozart's this huge choice that he has available. Let's talk about the brain, and now let's talk about a formal theory of art, because when you're talking about the computational hardware, we need to also talk about the algorithm. How does the algorithm play on that hardware, i.e. our brains, in terms of coming up with these choices? And the same way that company like Strata would process click streams with their machine learning algorithms, when we try to kind of create an analogy with the brain and our creative kind of thought process, there's a few formal theories out there, and one of the more interesting ones, at least in my view, is a guy, it's a German guy who is the director of the Swiss Artificial Intelligence Lab, and he created this theory of fun and intrinsic motivation. And the basic idea of that is that any creative choice we make is based on a reward feedback loop that allows us to process and compress historic data more efficiently going forward. So for instance, if your face is very, very different, I'm more inclined to look at your face for a longer time and try to figure out an algorithm that my neurons then encode, because that compression is in the future faster than the first time I encounter it. So, and he applies that to art, science, to many other areas of humans, but also he creates robots and bots, which he trains with that algorithm to come up with problem solutions that basically people like us encounter. So step by step, what does he say? So assuming that we could collect the entirety of our data stream as a human being, we then need to compress data so that it fits into our brain, right? So we basically create, let's say, the concept of beauty, as he calls it, is the concept that at any time a subjective observer can measure and can compress or describe data X at time T. And the bits of code, the number of bits that it requires to compress, that's what he calls the beauty. So that in itself is not really the interesting part. What's the interesting is the first derivative of that, which is basically that you create a continually updating processor where you are interested in finding compression algorithms that are incrementally better. And the supposition is that we as human beings, we kind of we run on this is our fuel. We kind of try to find out stuff that allows us to make these choices and process data more efficiently going forward. And what you would say, you listen to my colleague before was talking about Gangnam. That's a musical style, pop style, and you like it because there's a social context around it, but you also like it because the form of the music itself is relatively known. If I would play you like a Passacagli of Schoenberg, I mean, half of you probably leave the room. Why? Because the form of the music is so different that your brain finds it too much of an effort to code the compression algorithms because you are too many steps ahead. And the last thing it builds in is a reward action algorithm, basically trying to find out if any loop that this goes through can create a better improvement and therefore kind of stimulate the feedback loop so that you're ultimately ending up with a direction. And this could be a robot trying to go to walk, or it could be a robot trying to do visual pattern recognition. But it's basically a theory of art and creativity. Now, if you combine those two, and this is just another way, maybe if you don't like derivatives, then this is a simple way of describing the beauty bit versus the interesting bit, where the interconnectedness of data basically is the delta between one and the next compression analysis. So just to conclude, so if you were going back to Mozart and saying, here's 5-6 billion choices in that piece, how does his brain narrow down and actually process this stuff so that by the end of the day he makes choices, puts the ink on this dot and not on the other dot? Well, according to the fact that we have neural networks and not computational CPU-driven processing units in our brain. And the second element, that if you choose a formal theory of art, and let's stick with the one that I shown up there, then if you compare MapReduce based on the computing based versus neural based, the neural based is a memory retrieval process. But we get now to the most important bit, which is the fact that if you do MapReduce jobs in classical data science, obviously you run it in parallel, massively parallel computational clusters. If you run a neural network where your brain doesn't process stuff in a parallel fashion. There's a few parallel neurons firing, like you can do color, shape, and something else, but it's a very conservative parallel process. But what it is parallel, in a sense, if you collapse time onto one data point, and then your brain becomes a MapReduce machine, because you are in a loop solving a compression algorithm that becomes better and better by analyzing the same bit. And in this case, you say you can slice it between color, the shape of the face, and a few others. But ultimately, the parallel what I'm trying to make is that in our brain, you're looking at a sequential MapReduce process, which obviously is counterintuitive, but if you collapse it onto one time zero, then it becomes parallel, and as such, it's the same. I hope that made sense. Any questions?
Thanks, Thomas.
Thanks.